I will talk today about some theoretical and numerical problem for inverse problems on graphs, and mostly I will speak about trees, graphs without cycles, because for trees there are some completed, more or less completed results now. So it looks like this, and there are boundary vertices, and we will use boundary observations. I will talk about in more detail about our inverse data. And using this boundary data, we will try to recover unknown parameters of equations. So it is supposed that on each edge of the graph there are some equation and with unknown coefficients, and we recover these coefficients. And moreover, generally the topology of this tree is also unknown. This means that we are only sitting here on the boundary, and the root, one vertex is supposed to be fixed, but in any case we are sitting only on the boundary, and topology generally is also unknown. And moreover, some geometrical parameters, such as the angles between edges, may be also recovered, but this only for special kind of equations. So what kind of equations? So it may be just stationary Schrödinger equation. So was typical for quantum graphs, but quantum graphs are more or less new terms. But people were interested in such systems at least during the last 40 years. They called multi-link flexible systems or networks of beams or strings. So we may consider, for instance, like wave equation, and these coefficients may be unknown for and different for each edge. And moreover, in engineering practice, so if we consider this equation, it means physically that we have out of plane vibrations. So each edge, each string vibrates in this direction. But in engineering application, for instance, more important in plane vibrations. So it means that it could be in this direction and this direction. And in this case, on each edge we have two wave equations. So together with this, we have these equations, and generally it is different speeds of propagation, and they both may be unknown, and our problem will be to recover this using again some boundary observation. And certainly at all internal nodes, internal vertices, we suppose that some compatibility conditions. And today I will consider so-called standard compatibility conditions. So for scalar equation, it's just standard Kirchhoff equation. But for this vector equation, if we have two equations on each edge, the standard conditions looks a little bit more complicated, and these compatibility conditions involve angles between. Physically, it is the same. It is a balance of forces and continuity, but for these vector equations, this balance of forces and continuity involve angles between edges, and so angles are not irrelevant, and these angles may be recovered, maybe also recovered during using some boundary observations. And what is the main topic of this talk? In applications, in engineering, medical, and a lot of physical, technical, industry applications. So a lot of applications of graphs and equations on graphs, and typically the number of edges in applications very big. It may be hundreds, sometimes thousands, and and if we would like to solve numerically our inverse problems, the only way to solve this problem efficiently is to propose some kind of recursive algorithm. What I mean? I mean that we have originally our tree is very big, and we would like to recover it step by step, removing leaves. So on the first step, we will recover all parameters of this branch, and virtually we will cut this. Then this and this, and we use some inverse data. Yes, Weyl matrix function or the dynamical Dirichlet Neumann map. But on each step, we recalculate our data, and efficiently we reduce the size of our tree. So we remove leaves, and this in our point of view, this is the only efficient way which allows us to solve this efficiently numerically. But it is not so easy. It is rather tricky way how we can remove this leaves and recalculate our data and efficiently reduce our trees, and on the final step we deal only with one single rooted interval. And the methods which allows us to do this is a boundary control methods or boundary control approach. And the characteristic feature of this approach which allows us to remove these trees is this locality of these methods. What does it mean, locality? Locality means that it allows us to remove, so to recover coefficients here on this outer leaves. We use only data concerning this. So if we would like to recover only parameters of this part, we will use only this part of our data. So we can extract this specific part of inverse data concerning these leaves, use it, and then recalculate. And I explain how it works. First, on example of one interval or semi-axis, and I explain how this locality appears, how we can use this locality, and how this method connected with classical Gelfand-Levitan, Crane, and other classical results in inverse theory. So the first result in inverse theory was result of Victor Ambartsumian in 1929, and he proved, he considered interval and this equation on the interval, and with Neumann conditions, and he proved that if lambda n exactly n square, then Q is 0. So this is a classical result, and it is interesting. Bartsumian was not a mathematician; he was well-known astrophysicist, but nevertheless he proved this result. And but you certainly know that this is just exception, and in general only spectrum does not allow us to recover the potential. So generally we say, but I will today consider Dirichlet for Dirichlet condition for definite. It does not matter for our approach, but just to fix. So if we use Dirichlet conditions, then generally we need to know traces of eigenfunctions and, for instance, and eigenvalues. And this so-called spectral data, this set of pairs, allows us to recover uniquely potential of in this, for instance, problem. If we consider more general problem on semi-axis, then well-known Gelfand-Levitan result, which tells us how to recover potential. So instead of this discrete data, they use so-called spectral measure, which contains this information about spectrum and some, say, traces of eigenfunctions. And if we consider this equation with this condition, then it is known that this function related to just sine function through so-called transformation operators. So they introduce transformation operators and transformation kernels. So this function connected sine functions and phi functions. And so if and this spectral measure allows to relate what is yeah here. Ah, thank you. Okay, and okay, so it is convenient to introduce so-called regularized spectrum. So we just subtract function which correspond to zero potential. Okay, and then they construct function f. So if rho is known, sigma is known, so we can introduce this function, and after that they derive famous Gelfand-Levitan equations. So this f is known, so we find k, and after that so very nice, beautiful and well-known equations. And it was also known and noticed that this kernel's transformation, kernel's k satisfies so-called Gursa equations, and Levitan used this fact in some papers, but not maybe not so much, but this is very important. It is well known, but it was published 51, and it is well known, but not so well known papers by Crane. He published a series of papers in the beginning of 50s, and especially two papers published in 53 and 54. Mark Crane, yes. Mark Crane, yes. It was published in Soviet доклады of Soviet Academy of Science, and unfortunately these papers not so known. Approach is quite different. Roughly speaking, this result is some kind of perturbation theory, because they compare this equation compare with equation with zero potential. Crane's approach is quite different. No perturbation theory, and in some sense it's more general result, because it allows to recover not only Q but also rho. For instance, it is more some say more complicated problem, and his approach is based on theory of so-called direction functionals, which was developed by himself in the middle of 40s, and unfortunately, but it is very complicated theory, and it is not so known, because complete results with all details never were published, and never were published. But nevertheless, in 71, Alexander Благовещенский published proof of Crane's results using so-called local or dynamical approach, which is very similar to approach to boundary control method. So Blagoveshchensky was a pioneer of the local approach. Again, what does it mean local? So this Gelfand-Levitan is not local approach, because we use information spectral function which is given for the whole semi-axis, and recover immediately potential the whole semi-axis. And it is not clear if we would like to recover potential only say on this interval, what part of information, how to separate this part of information if we would like recover only this. It is not clear because it is typically spectral approach. It is typical for spectral approach. Yes, it's not so easy. If we have a function supported only on the part of interval and make a Fourier transform, it is not so easy to recognize that support is only here. So it is a typical for spectral approach. Okay, so Blagoveshchensky proved Crane's results using dynamical approach, and and in 1999 Barry Simon proposed his new approach to inverse theory, which is local, but his method is spectral. But results he obtained some local results. So he introduced so-called A amplitude. A amplitude. Why? One more important thing. So Gelfand-Levitan, they use as a data, they use spectral measure, and you see, certainly it is not a problem to solve this equation. It's a linear integral equation. But if we would like to produce a series of numerical experiments, we should know our inverse data. Inverse data, spectral measure. So we have to be able to solve efficiently direct problem. So given potential to find spectral measure, and numerically it is funny things, but numerically it is much more difficult than to solve linear equation. So numerically we should to produce spectral measure. Okay, it is huge problem, and so in physics, so it's not so efficient data spectral measure, and turns out that Teichmans-Weil function much more useful in many theoretical problems, and therefore Simon decided to start with Weil function instead of spectral measure to solve inverse problem using Teichmans-Weil function. Certainly, M function and spectral measure are in one-to-one correspondence. So mathematically, it is equivalent data. But but to recalculate them, it is again very difficult. Okay, and so they started with this while function, and he proved that there exist in unique this real valued function a, which is roughly speaking Laplace or Fourier Laplace transform of the path of this path corresponds again zero potential. If potential is zero, we do not have this. We have only this, and this is a Laplace transform of this combination. Okay, so he proved existence and convergence of this integral for some class of potentials, and then so his way is the following: is if M is given, then we can subtract this part, take an inverse Laplace transform, find A, and if we find A, then we can find Q. But his equation, how to find Q using A is not linear. It is non-linear equation, and certainly it is much more difficult to solve this non-linear equation comparing with linear Gelfand-Levitan equation. Nevertheless, he proved locality. So he proved that a function given on interval uniquely determines Q on the same interval, and vice versa. So it is a local connection between A and Q. And he asked a question. He felt that his approach somehow related to Gelfand-Levitan, but could not find this connection. Okay, and now from this fact, he proved so-called local version of the Marchenko-Borg theorem. So in 49, approximately, Marchenko and Borg independently proved the fact that Tishmer-Schweil function uniquely determines the potential. And Simon proved a local version of Borg-Marchenko theorem. Namely, he proved that this asymptotic relation, so if we have two M functions and they, if we have this asymptotic relation, then our potential coincide on interval 0A. So this is a local version of the Borg-Marchenko theorem. Okay, and so, but again, all these three theories, Gelfand-Levitan, Crane, and Simon, are tremendously complicated. So they were published in on many pages, and all proofs are very complicated. So Simon, Gestede, Simon, they published two huge papers in Annals Annals of Mathematics. Crane never published completely his results, and even original Gelfand-Levitan proof was also rather complicated. And but already the local approach of Blagoveshensky in 71, he's proved much of Crane's result, much more simple. And but using boundary control approach, all these results can be proved in just 3-4 pages. So in very simple way, all completely, all results, all theories, Gelfand-Levitan, Crane, and Simon, and even more results can be proved. So what was the idea of this boundary control method? So we consider corresponding wave equation. So on semi-axis with zero initial data, and say Dirichlet boundary condition, and we call this function control. And as inverse data, we introduce so-called dynamical Dirichlet to Neumann map, or response operator. So we introduce this. So these are, in terms of system theory, this is our input, this is output. So it is input-output map, dynamical Dirichlet to Neumann map. Okay. First of all, it is clear that this map, dynamical Dirichlet to Neumann map, related to the Weyl function just through Laplace or Fourier transform. It is clear. If we take a Fourier or Laplace transform of this equation, we obtain this equation, and this dynamical Dirichlet to Neumann map transfers to spectral Dirichlet to Neumann map to the Weyl function. So it is clear that we have this relation. And what else? It is very easy to write a representation for solution this equation. If Q is 0, how to write the solution? If Q is 0, this is the exact solution, evidently. If Q is not 0, we should add some integral term. This formula can be found in any textbook on PDEs. So speed of propagation is 1. It is clear speed of propagation is 1. So for x greater than t, our solution is 0, because our initial data only we produce a wave from the boundary. Okay, and this is a representation of solution, and this function w satisfies well-known Goursat equation. Well-known Goursat equation. So it this Gaussian equation, and okay, it is clear. If we find this solution, we immediately obtain Q. Okay, and we can differentiate this formula and put x equals 0, and we obtain a representation for this response operator R. So again, if Q is 0, we have only this term plus convolution operator. So this small r response so-called response function uniquely determines our operator. Okay, and so so if we know R, so our problem if to find inverse problems, given this function small r, to find potential Q. Why our function, why our approach is called boundary control approach? Because controllability plays important role, and what does it mean, controllability? In this situation, it is very simple result. It means that using our control F, so we introduce so-called control operator as a okay, and using this representation, we see that we can get any function here. So if we prescribe any target from L2, we can get this function using this control, because this equation may be considered as a Volterra type equation for F. Okay, so and and using this controllability, we can consider special control problem. So to get to solution of this equation. So find control that our function u can coincide with solution of this equation, and then we immediately obtain equation which coincide with the Crane equation. So this equation okay, when P of t just integral of this function. So when we solve this equation, we find F solution of this equation, and using this solution, if we then we immediately obtain this equation. So using this boundary control approach, we in very simple way we obtain linear equation for finding our potential. And moreover, again, using this approach, we can derive so-called local version of Gelfand-Levitan equation. It is interesting thing that Gelfand-Levitan equation can be written almost in this form. So the main part is the same. Only the left-hand side is the same. Only the right-hand side is different. So nobody notice that Gelfand-Levitan and Crane equation essentially the same. So the kernel is the same. But what is important that this kernel is local. So this kernel is constructed through this function R, and R is completely determined. And this function R related with Simon function in very simple way. But in Simon approach, his A amplitude was some kind of mystic. So nobody understood physical meaning. But physical meaning of this response function is a very simple. Very simple. It's just a kernel of the Dirichlet-Neumann map. Okay, so the point is, so it is a local approach, very simple. And how now we apply this for graphs? Because it is local, so we can use any kind of inverse data, while function, spectral data, or dynamical response operator. But because of locality, we can recover potential on these leaves, and then using standard compatibility condition, we can efficiently recalculate our data and reduce this operator. So the point is that this approach, because of locality, allows efficiently to remove leaves of the tree and recalculate inverse data. Thank you very much.
Thank you very much. Any questions or comments? You said that you have some numerical data. Can you show something, or it is not on your computer?
Oh. No, I cannot demonstrate, unfortunately. But yes, for simple graphs, yes, we have already some numerical data. So we started certainly with simple star graphs, but it works. And if what about the data for one interval? Yes, it was already published earlier, and it works rather well.
Okay, thank you very much. So thank you.